Hi there, welcome to just another dev. And today we are going to talk about doubly linked list. So in our previous video, we have already covered about linked list. And if you are not aware of linked list, you can go back to that video and see what is a linked list. So talking about doubly linked list is nothing but it is very similar to the linked list that we discussed in the last video. The only difference is linked list has only one reference to the forward node, but in doubly linked list, it has a back reference as well. So if you see there are different nodes over here, and if you see this pointer, right, so if you see this link, so this node has a forward reference to this next node. Also the next node has a forward reference to another next node. Also it has a back reference as well, right? So you see this 15 has a back reference for 8 as well. This 20 has a back reference for 15 as well. Obviously the first and last node will not have the back reference and the forward reference by default, because this is going to be null, right? So here you will see only forward reference. This doesn't have a back reference because this is the head, and this one will not have a forward reference because this is the tail. Also, if you have a particular node reference, right, you know the reference for this particular node, you can simply delete it because you have all the references in place. It has the forward reference, back reference, and the forward reference, back reference. So you can simply remove it here without having any knowledge of the other neighboring nodes required. Yeah, so this is one other advantage. And it is used by web browsers to maintain forward and backward navigation. So basically the web browsers use linked list or the doubly linked list to maintain the history and all. Also it is used in a very popular cache called LRU, where the caching policy is implemented using doubly linked list, right? So the LRU cache policy internally uses doubly linked list. Okay, so let's move ahead and see how we can implement a doubly linked list. Okay, so now let's create a doubly linked list. So I'll just create a folder, and the first thing that we are going to do is we are going to create a list node for the doubly linked list. So I'll just put it doubly linked list node, just it's a doubly list node itself. Now in this doubly list node, what we are going to do, we are going to have two things over here. First thing is obviously the value, that what value we are going to assign to this particular node. Also it will have both the forward and back reference. So let's just call it next and previous equals to null, and we are just going to export it. Okay, so this is what we have done. We have created a constructor function for this doubly list node. We are going to accept the values, we are going to set the value, and the next and previous are by default set as null. Okay, now let's create a doubly linked list. So in order to create a doubly linked list, we are going to create another constructor function, doubly linked list. We are going to initialize it. So we are going to say, okay, the size is initially 0. We are going to have a head. And if you remember earlier that we talked about sentinel nodes. So here also we are going to create sentinel nodes, which are basically dummy nodes. The reason again why we used to create these sentinel nodes is because we don't have to keep explicit check that if the head is present or the tail is present, or if you're setting them as null, if you don't have any head or tail to point to in the beginning, right? So when you're going to add your first element or the first node in your doubly linked list, you will have to point the head to that and the tail to that particular node. So we don't want that all that overhead. So we are going to create two doubly list nodes. And initially, let's say I'm going to give them value 0. Let's say same thing for the tail as well. So we created two sentinel nodes here. Also this dot head dot next, I would say, because we have to join these, so the head is pointing to tail. Similarly, tail will be pointing to this head. So what we have done over here is we have created something like this head. it's pointing to tail. So it's basically forward and backward connectivity between them. Okay, now this is basically how we can initialize our doubly linked list. And now let's see how we can add different methods to it, like adding at a particular index, adding a node at a particular index. Let's add a method to add at a particular index, add a node at a particular index. So add at index, we are going to doubly linked list dot type dot add at index. This will basically be a function which is going to accept the index and the value. So the first thing we are going to do is we are going to check if the index is valid, index smaller than 0 or index greater than size. Actually it should be this dot size, so let me just do a destructuring so that I don't have to worry about this mentioning at size instead of this dot size. Okay, so if the index is out of bound, we are just going to return, we are not going to say anything. But let's say we have a valid index. Now what we are going to do, so I'll just create an example over here. So this is the head, this is these are our nodes 4, 5, and then let's say we have this tail. Okay, so one thing about doubly linked list is that you can traverse either from the front or from the back, right? So it is a good idea that we can find out where we are closer, right? So if we are closer to the head, we can traverse from here, but if we are closer to the tail, we can traverse from there as well, right? That's the advantage of doubly linked list. So let's see a couple of examples. What if the index is 0, right? So the size of this is basically 1, 2, 3. Okay, and from the back, if we have to add it at index 0, we'll have to reach in between this, right? So what we'll have to do, we'll have to reach at this 1, 2, 3, we'll have to come over here. Okay, so it obviously makes sense that we move from head in this case, right? But what if the index was 0, 1, 2, 3? Let's say we have to add it at index 3, size is also 3, so then it makes sense that we move from here, right? So what we are going to do, we are going to take an advantage of index. This is the index, this is size, and then we are going to calculate size minus index. So in this case, size minus index is what? 3, right? So what we'll have to do, we'll have to come till this 1, 2, 3, right? After this, we can figure out, okay, now this is the place where we'll have to add it. Okay, so basically we are keeping a track of previous node when we are moving from head, and we are going to keep a track of successor node when we are moving from tail. Similarly here as well, size minus index will become what? It will be 0. This is the index, this is the size minus index is 0. So basically what we can say, we don't have to move anything, so we have the successor over here, and obviously the predecessor will become this thing, or the previous will become 5, the successor will become this tail. Okay, so let's bring this to the logic. So initially what we are going to say, the previous node is always head, and the next node or the successor node is always tail. And we are saying if the index is smaller than size minus index, basically we are checking if we can move from front or move from back, right? So index is basically is obviously smaller than size minus index, so we are going to move from front. And what we are going to do, while we have this index, we are going to move our previous node to the next node. So let's take an example of 1 maybe. Index is 1, size is 3, size minus index is what? 3 minus 1, that is 2. So we fall into this case, this is correct. Now what we are doing, since the index is 1, we are going to have one iteration, so we'll move from here to here, right? This is index 0, right? Because we don't consider this head and tail, these are our sentinel nodes, so the dummy nodes that we created. Our actual linked list start from here, right? So 0, 1, 2. So if we have to put it at index 1, we are coming to this 3, which is going to be our previous node, right? And we'll have to insert it here. So that's what we are doing. So while index, we are saying previous equal to previous dot next. I'll do an index minus minus. And now since we have reached till this 3, we can say our next node is what? So next is previous dot next. Okay. So when we are coming from this, we got our previous as 3 and we set the next node as 4, which is correct as well, right? Because we have to insert it at index 1. So to put it at here, this index 1 position, we are going to say previous is this and the next is 4. Okay. And when we were coming from the back, in that case, what we are going to do, we are going to say size minus index. So consider this case, right? This will not fall into this, but let's just consider this case for now. Imagine if you're coming from backside, right? So index is 0. If you want to add at index 0, size is 3, size minus index is 3. So what we are going to do, we are going to make 3 iterations. So 1, 2, 3, right? So we have reached what? We have reached our successor because we want to add it at index 0, right? So it has to be inserted between head and then this 3. So coming from the back, we are iterating 3 times, which is basically size minus index. If it was index 2, let's say, or maybe 3, yeah, this case only, then size minus index is 0. We don't have to do anything, right? So if it has to be inserted at index 3 and basically 0, 1, 2, 3, somewhere near here, size minus index is 0 already, so we don't have to traverse at all. So this is our successor and our predecessor or the previous node will become this 5. So this is what we are going to do here. So here we are going to say, okay, next equals to next dot previous, and here we are going to increment the index because we want to make this thing as 0, right? So okay, yeah, now what we are going to do here, we are going to put this thing as next dot. Okay, next we already are moving towards, we need to set the previous equals to next dot previous. Consider this case again, right? This thing, yeah. So let's say if we are moving from back, so we came till this, right? 1, 2 and 3, and since we have to put it here at index 0, so this is basically our successor or the next node. What will be the previous node? So the previous node will be this next dot previous. So that's what we are doing over here. Okay, so now we have got our next and previous nodes. It is time to add a node in between. What we are going to do, we are going to create a new node, doubly list node with the value, and now what we have to do, we have to, let's say, insert it at this position or whatever the position is. We have already calculated the previous and the next node. Now what we need to do, we need to add something over here, let's say a particular node. What we are going to do, we are going to say this new node dot previous is basically pointing to previous, so it is pointing to here. New node dot next node is pointing to the successor. Also the previous node will be pointing to this new node now, and the next node will be pointing backwards to this new node. So this is what we did here, right? We created a node, we said okay, this will point back to this and forward to this, right? New node dot previous equals to previous, new node dot next equal to not successor, it should be next. Let me check if I'm using successor anywhere else. Okay, I'm not using, fine. And yeah, the next thing that we are doing is previous dot next. Basically this dot next, we are setting it as new node, and finally this next, which is this 5.previous is, we are pointing to this new node that we just created. So this is how basically we can insert a node at a particular index. Also, one last thing that we have to do is we'll have to increment the size. So here we are incrementing the size. So this is how basically you can add a node at a particular index. Also, if you want to extend it to, let's say, add at beginning or add at end, you can simply call this add at index from there with providing the index as 0 or size, depending upon you want to add it at the beginning or the end. So that is nothing but an extension of this. We can implement it directly as well, but this is basically the essence. This is how we are going to implement it. Okay, I'll just show it to you. Let me just put it add at, let me call it add at head. Here we don't need index. So either I can write the code over here, or I can just simply say return this dot add at index, and if we are adding at heads, obviously the index will be 0, and I can just do this. So instead of completely writing it again, I can just simply call this. Same thing we can do for add at end as well, or add at tail as well. Here I will just pass the size, so it will become this dot size. Okay, now let's see how we can delete a node at a particular index. Before that, let's implement get as well, which is also going to be very similar. So doubly linked list dot prototype dot get at index. This will also be basically a function, and it is only going to have this index over here. Similar thing we'll be doing here, null checks and everything, the size bounds and everything. So I'll just copy paste it from here. We can remove whatever we don't need. Okay, so if basically the index is smaller than 0, or if the index is greater than equal to size, right? Because if we are going to have this index from 0, so it cannot be equal to size. So 0, 1 and 2 in this case, it cannot be 3, which is basically the size of this, right? Because 3 we don't have anything. So just a little bit tweak here. So index is greater than equal to size, we are going to return, let's say we return null over here. We don't find that value. Now similar thing we can do, if we are going to get it from front, or if we are going to get it from back. So here also we are going to say previous is pointing to our head and next is pointing to the tail. A slight change here, if we are going to go to index 0, we will have to iterate till the index becomes 0. While the index is greater than equals to 0, we are going to say okay, previous equals to previous dot next. So for example, if the index was actually 0, what will happen in this case? We'll move from this to this, because we have changed the iteration and we are setting it as greater than equals to 0. So even when it is 0, it will still iterate for one go. And yeah, we can just return this value. Let's just call it node here. Okay, because in this case we are iterating from here, we don't need to remove or add anything, so there is no point having this previous and next as of now. So what we are going to do, we are going to say okay, this node equals to this dot head, and we are moving towards the next node, and then when we reach there, we will return this node. Otherwise, if we are traversing from back, let's say this is the case, again we'll take this case, we can check basically the size minus index. Let's say if we are iterating from back in this case where the index is 0, and if you want to iterate from back, what we can do, we'll have this initial pointer at here, we'll have the node at pointing to this tail, and then the size minus index in this case is basically 3, right? So we'll iterate 3 times, so 1, 2 and 3, and we'll reach this node in particular. Also, what if let's say we want this node the index is 2 in this case, size is 3, right? So size minus index becomes what? It becomes 1. So we'll iterate only one time. We don't have to set it as greater than equal to 0. We only had to do it here because we wanted to reach that particular node. So in this case, we'll reach that node itself. Here also I will say this dot previous, this dot tail, not previous, and node will basically be node dot previous. We'll move previous and we'll keep on incrementing the index. Here we are going to return this particular node. The rest we don't need anything here. So this is basically how we can implement get. So delete is going to be very similar to get. So I'll just copy it from here, because once we reach that particular node, we can delete that as we have the forward and back references. Here also we'll have to use the same thing. If the index is out of bound, we can't do anything. We'll return null. And again, if we are going to move from front or back, so what will happen in this case, since in get we were reaching that particular node, right? So this is the same code. We have reached this particular node. So I'm just going to call it node to delete. Just make it everywhere node to delete. Okay, now instead of returning it, what we can do, okay, so we created this node to delete equals to this dot head. If we are going from forward, it is fine, but if we are going from back, we set it to tail, and then we basically move to the previous nodes. So now that we have got this node to delete, let's get the previous one. Previous node equals to node to delete dot previous. Next node equals to node to delete dot next. Now what we can do, let's say if we want to delete this node, right? So if we are here, what will happen? We need to delete this reference. So this previous dot next should not be pointing to this. So what should happen? Previous dot next or previous node dot next should point to next node. And similarly, this next node dot previous should point to this previous node. Okay, so this is basically what we have done. Let's say we were here, we wanted to delete this, we got these references 3 and 5, and we have basically setting this previous node dot next, basically this dot next to 5, which is our next node here, and from here this dot previous equal to this one. So this is how basically we have broken this link with 4. So this forward link is broken, this backward link is broken, and we have set them like this. Also we can break this link as well. So basically this 4 is still pointing to this 3 as a backward and 5 as a forward, right? So even though we have broken the other two links, the rest two links are still there. So what we are going to do, we are going to say node to delete dot previous equals to null, node to delete dot next equals to null. This will basically break all these links, right? So there are 4 links, right? 2 we interchanged and 2 we deleted. So now this 4 is isolated, and finally we are going to decrement the size. We are going to decrease the size. So this is how we can basically delete a node at a particular index. We find that particular node just like what we were doing in this get, and then we finally delete this by deleting these references. Okay, let's see how we can test it. I'll just create another file called test.dll.js. Now what we are going to do, we are going to create a doubly linked list. Okay, I think I'll have to export it as well. Okay, we got our doubly linked list here. Now what we are going to say, we are going to say add at head, let's say 4, add at head again 5, add at head again 6. So by this time it should have become 6, 5, 4. We can do a console log as well. So let's try to run this. So, test dll.js. Okay, so let's see what it is. Okay, so we have initially 6. It is showing 0 because if you remember we had a sentinel node where we pointed it where we set the initial value as 0, right? So it is showing you 0. Then it is showing you 6 because we keep on adding at head, right? So our initial node, the first node, is basically 6. Then we have 5, and then again it has a doubly linked close, but it is not printing it because there is only a certain level of depth we can print. So what if we do this head.next? Let's see if it prints now. Okay, yeah, so we see this 654 because we keep on adding at head 654. Now let's say if I add something at index, so our 0th index is basically 6. Now if I add at index 1 value 12, let's see if it is going to work or not. Okay, sorry, I forgot to print it again. Let me just remove it. Okay, so now at our first index it has become 12, then 5, then we have 4. Cool, so this seems to be working. Let's delete something. So let's delete at index. What we have 1, 2, 3, 4 items. So let's say we want to delete at index 2. So ideally we have 6, 5, 4 and 6. At this point it has become 6, then 12, then 5, then 4. So ideally we are deleting at index 2, so it should become 6, 12, 4. Let's see if it is working or not. Okay, we got an error. Previous node dot next equals to next node cannot set property of null. Setting next. Let's see what it is talking about. Okay, so we have got the node to delete. Okay, so the reason why, because I did not use that node to delete over here, I was using node only. So hopefully it should be fine. Let's see again. Oops. Previous node dot next equals to next node. Same error. Let's print if we are getting the correct node or not. Node to delete. Okay, so the node to delete that we have is Not to delete it is showing 0. This is okay, my bad again. I shouldn't have used let over here, so we have to use the same variable. Hopefully no more errors. Okay, cool, seems to be working fine now. So now the node to delete is basically, where do we go, test DLL. Yeah, so we wanted to delete 5, right, because we are saying okay, deleted index 2 0 1 2, so it is 5, so the value is 5, and again it is showing the next value as 4 and all. So now what we are having over here is 6 12 and 4, which is expected, right? 6 12 and 4 because we deleted 5. And if one last thing, let's see if we want to use this get at index. So if we want to see what it's present at index over here, just do a console.log get at index 1, so it should ideally return me 12 now. Let me just put dot value so that we can see clearly. Okay, so it is returning as 12. So this is working fine. So that's how we can implement our doubly linked list. And now let's move on to see the time complexity and space complexity of doubly linked list. So let's talk about the time complexity of a doubly linked list. And the time complexity of doubly linked list comes out to be O of n for operations like insertion, deletion, and accessing a node by an index, because you will have to traverse through the linked list and figure out okay, this is the node or this is the particular index that you want this operation on, right? You want to insert at particular index, you want to delete a particular index, or you want to access something at a particular index. So the time complexity comes out to be O of n. And you can argue that okay, if we have a flexibility of traveling from front or the back, but if the linked list is big enough, then those differences do not matter that much. So the time complexity still comes out to be O of n. If you are inserting or deleting at the beginning or in the end, then obviously the time complexity is O of 1 because you don't have to traverse it. But if we talk about the general time complexity for the worst cases and all, so it will always going to be factor of O of n, which is basically a linear time complexity. The space complexity on the other hand is going to be O of 1 because we don't need any extra space for implementing these, right? You can go ahead and insert any element and it doesn't matter how big or small is your linked list. You need a constant space for it because you are not doing any operations like saving it in another data store or basically another data structure or anything. You are not doing anything like that. So you just need to traverse and you need to do these reference changes, that's all. So the space complexity is O of 1, the time complexity is O of n. So that's about the space and time complexity of doubly linked list, and thanks for watching. Stay tuned.